Hey everybody, Dr. A again, and in this example, which is the fifth example of us solving equation systems by substitution, we are going to be solving a system of three equations with three unknown variables using substitution. So let's take a look at this given information and make sure we're all seeing the same thing. Our first equation is x minus 2y plus 3z equals 9. Our second equation is negative x plus 3y equals 4. And our third equation is 2x minus 5y plus 5z equals 17 here. So just to help be organized, I'm going to label these equations 1, 2, and 3 here, okay? So to go ahead and get started, we're going to follow the same rules that we've seen before with the substitution method. So under solution, the first thing I'm going to do is I'm going to solve for one of my unknown variables in terms of the other two variables in one of my equations. And as you've heard me say before in some of my other substitution example videos, it does not matter which one of these equations you want to start with, and it does not matter which variable you want to solve for first in terms of the others, okay? So one thing to notice is how I've written this in an organized way that can maybe help us determine what's a good starting point. So notice that I've written all my terms or my expressions with the variable x. I've kind of written them in an organized way where they're stacked on top of each other. I've written all my terms with the variable y in an organized way such that they're stacked on top of each other, and then a similar way with z. And if you notice, this second equation actually does not have a z term here, okay? So let's think about it. Maybe pause the video and think about it on your own. Which equation do you think would be good to start with and solve for one of the variables? So pause the video, think about it. Okay, I'm going to tell you. I personally, and again, it doesn't matter, but I would start with equation 2, and I would solve for the x variable in terms of y in equation 2. Again, you don't have to, but the reason why I would do that is because equation 2 does not have a z variable, and so algebraically, it's a bit easier to rearrange equation 2 in terms of x equaling everything else compared to 1 and 3. But again, you may take a different approach. So I'm going to start with equation 2, and I'm going to solve for x. So if I rearrange equation 2, I'll get x equals 3y plus 4. Okay, so I'm just moving this x to the other side of the equation, and I'm moving the 4 to the other side of the equation. So now I've solved for x in terms of y for equation 2. Now what I'm going to do is I'm going to sub this into equations 1 and 3. Now, it may be a good idea for you to color code things. I do better when I color code my work in my calculations. I can just see things better. So when things get a little mathematically tedious and messy, I like to color code. So maybe a good suggestion for you. But either way, I'm substituting in this equation 2 into both equations 1 and 3. So let's do this one at a time. Let's go to equation 1 first. And let's substitute this into equation 1. So where we have the x in equation 1, we are going to replace that or plug in 3y plus 4. So I'm going to say 3y plus 4 minus 2y plus 3z equals 9, okay? So that's my new version of equation 1. And in a similar way, I'm going to get a new version of equation 2 by doing the following. I'm going to have 2 times 3y plus 4, close that parentheses, minus 5y plus 5z equals 17. So this is the new versions of equations 1 and 3 with equation 2 substituted in for the x term, okay? Now I'm going to do some simplifying, okay? So let's go back to equation 1, the new version of it, that is. So I'm going to I'm going to simplify this equation 1 out just a bit so I can gather my y terms, and we'll have 3y minus y here gives us just a positive 1y, and then I'll have plus 3z, and I'm going to move that 4 to the other side of the equation. 9 minus 4 gives me 5. So that's my simplified. I simplified this version of equation 1 down to y plus 3z equals 5. Now I'm going to do a similar thing. I'm going to simplify this equation 3. Don't forget, you have to distribute this 2 here. You got a distributive property you need to execute. So that'll be 6y plus 8 minus 5y plus 5z equals 17. And again, equation 3, we need to do a couple more steps of simplification. So I'm going to continue labeling things to make my life a little more organized. 6y minus 5y, that gives me a positive 1y plus 5z. And I'm going to move this 8 to the other side of the equation. So I should get 17 minus 8 gives me a positive 9 right here, okay? So what do we have now? If you look carefully, I'm going to make a note here. I'm going to put a little star here. Now, equations 1 and 3 represent 2 equations with the same 2 variables. And what are those 2 variables? Y and z. Okay, so now what I can do is I can solve the simultaneous equations 1 and 3 as if they were just 2 equations with 2 variables. Okay, so I'm going to rewrite them just to, again, keep myself organized. Again, being organized with this is kind of a key to success here. It's easy to kind of get lost in the sauce if you're not careful. So I got y plus 3z equals 5, and then equation 3 is y plus 5z equals 9. And again, I'm going to do a similar substitution process. I'm going to say solve for y in equation 1 in terms of z, and then I'm going to substitute that. So I'm going to say then sub into equation 3. All right, so let's rewrite equation 1. So we're going to say y equals negative 3z plus 5, and then go to equation 3 here, and we're going to substitute that into equation 3, and that will give us negative 3z plus 5 plus 5z equals 9. And so in equation 3 here, I'm going to solve for z. Look at that. Equation 3, I just have one equation now with one single variable z. I've substituted a couple of times to reduce down to one equation with one variable, okay? And so equation 3 now can be simplified to 2z equals, and again, we're going to say 9 minus 5, okay? So 2z equals 4, z equals 2. This right here is part of our solution, but we're not done yet. We need to get the whole solution. That means we need to get a value for x and y. So now I can substitute z equals 2 into an earlier equation to solve for y. So if you just look at this immediately earlier version of equation 1, you can utilize that. We can say utilizing this version of equation 1, we'll have y equals negative 3 times 2 plus 5. And so sure enough, y equals negative 6 plus 5 is negative 1, okay? That's another part of our answer. And finally, we need a value for x. So what we can now do is use either y or z and substitute into one of the earlier equations. Take a look at this convenient version of equation 2 from the beginning of our solution. X equals 3y plus 4. So watch this. We can now sub z equals 2 and or y equals -1 into an earlier equation to solve for x. Okay, so let's look at an earlier earlier version of equation 2. Again, we can use x equals 3y plus 4. So let's write that down. X equals 3y plus 4, just to remind ourselves of it. And then we can substitute that value of y in here. 3 times -1 plus 4, so x equals 1. And finally, our solution is x equals 1, y equals -1, and z equals 2. You know, you can also express a solution to a system of equations as either an ordered pair or an ordered triple. In this case, since we have 3 equations with 3 unknowns, we could also express the solution as open parentheses 1 comma -1 comma 2 if you'd like. So that's either way, that's the solution. And that concludes this video. Thanks for watching.